So let's have a look at some of the improvements in technology. On the left-hand side, we have conventional Doppler ultrasound. This is the transducer just here, and the transducer operates in a transmit mode. It transmits a beam, and then in a receive mode, it receives a beam. And in this case, the transmit and the receive is along the same beam direction, measuring just one velocity component, that along the beam direction. So here is a typical conventional Doppler ultrasound, just using a single beam with a single spectral Doppler trace. On the other side, we have our vector Doppler system, where we've now got a single transmit that was split in the aperture into two to receive two beams. So we've now got two velocity components, and with a very simple little bit of maths, these can be combined so that the velocity magnitude and the direction are estimated automatically. And this is some of the data using a prototype vector Doppler system, which we got from one of the manufacturers. And we're using a phantom here. So this is, I'll talk about phantoms in a second. This is a phantom, which is a mock-up of a diseased artery. You can see the narrowed segment just here with some waveforms. I'm going to measure the velocity of these waveforms. And in the middle, we've got the conventional single beam Doppler system, and the true velocities are shown as a line. And in all cases, the Doppler system is overestimating these velocities, as you can see, often by large amounts. So the same experimental setup using our dual beam vector Doppler system. This time, the measurements are quite tightly contained, and they're all around about the right value. So use of this two beam system is vastly increasing the accuracy of the measurement. So that certainly helps. Right, moving on a few years, this is data from Pei Yang, who's currently based in Shanghai, writing up his PhD, and he's making measurements of wall shear stress, as we can see. So this is using a vector Doppler system. Again, we've got phantoms here being used to undertake the validation. Velocity measurements in the middle with the little arrows showing that the velocity direction, and the wall shear stress values being shown on here, showing that this type of technology can make these measurements, and hopefully we'll go on to make these measurements in patients. So this is wall shear stress, which I said was associated with the initiation, development of disease, and plaque rupture. So I've talked about the need to measure 7D flow, and computational fluid dynamics is a fantastically powerful tool for measuring 7D flow. And the way this works is that you need 3D data set, you need 3D geometries of the arteries. And in this case, we're going to collect this data using ultrasound. And what we've got is our ultrasound scanner. We've got our transducer just here, and you can see we've attached this little thing here to the transducer, and this has got light emitting diodes on, which are being tracked in space by this camera. And so as the transducer is moved along the artery, so the camera knows exactly where the transducer is and can build up a 3D data set consisting of lots of 2D slices. So this is exactly what you're looking at here. You can have a 3D data set as the transducer is being gradually moved along the carotid artery, going from the common carotid artery through into the bifurcation where the disease is. You can see the disease just here, and then into the internal and external carotid arteries. So we get our 3D data set. This goes through an image processing technique to segment the data and mesh the data, and then this is passed to a computational fluid dynamics solver in a computer, which will calculate these velocity streamlines, the velocity profiles, and the wall shear stress. So this is our 7D data that we need. So now moving on to phantoms. A phantom is used for validation of ultrasound measurements, and this is a typical phantom as it's used in the lab. We've got this kind of grey agar-based tissue mimic just here with a channel running through it. The transducer is held in a retort stand and clamp just here. And we've got this picture up which I've already shown. This is a phantom of a diseased vessel with waveforms just here. So the phantom typically consists of three different components: a tissue mimic, a blood mimic, and a vessel mimic. And these need to have very similar properties to the acoustic properties of tissues in humans. So the specific properties that need to be mimicked were specified by an organisation called the International Electrotechnical Commission some time ago. And this is the density, the speed of sound, the attenuation coefficient, and the viscosity. So my lab has spent a lot of effort making tissue mimics, blood mimics, and vessel mimics, which have got the correct physical properties. So starting on the left-hand side, the original agar-based tissue mimic, as you can see, is relatively weak, and it splits very, very easily. Now, this is a problem if the vessel is quite close to the surface, or if the anatomy is complex and the phantom will rupture. So we spent some time developing a much stronger material based on konjac carrageenan, and these are chemicals used in the food industry. And as you can see, it's not splitting. In the middle, we've got blood mimic, and this is the white blood mimic that we developed based upon nylon particles as used in the paint industry. And this has become the international standard blood mimic used all over the world. And on the right-hand side, we've got a vessel mimic just here. This is this grey material, this grey pipe, which is embedded in this yellow tissue mimic just here. And we're interested in the motion of the tissue. As you can see, the vessel mimic is here just pulsating nicely as an artery would do in the living body. So phantom design, the easiest phantoms to make, flow phantoms to make, are straight tube phantoms. But as we've seen, flow in arteries can be very complex. So what we'd ideally like to do is to make phantoms which have got complex geometries. And this comes from a collaboration we had with Liverpool University, and they used what was then called rapid prototyping. The phrase 3D printing now has begun to encompass a lot of that. It was known as rapid prototyping at that time. So we start off with a solid model, an idealized CAD file on the left-hand side, which has been taken using MRI and then idealized. This goes through a stereolithography process to make this solid model at the top. This then gets incorporated into a silicone mold to make the mold, to make the silicone mold. Once the silicone mold is made, you can pour low melting point alloy into the mold, let that set, take it out, polish it up, put it in the box, pour in the tissue mimic, let the tissue mimic set, melt out the low melting point alloy, and you're left with a channel through the tissue mimic, which has got the proper carotid geometry. And as you can see here, I'll just wait for it to go around. So going from the common carotid through into the internal and external. If you look closely, you can see this is pulsating. This is being driven by pulsatile flow. And this is typical, this pulsatile motion is typically what you get in carotid arteries in vivo. And even though this was published 15 years ago, this remains the best work to date in the area. So what the next step would be to take a 3D printer and to directly 3D print all of this, but this is still remains the domain of research, really. So, quick summary of my research. Where are the opportunities for Dundee? This is Colin Murdoch. Colin Murdoch has just got a big grant, $380,000 awarded from the MRC to purchase a Vivo 2 ultrasound scanner for preclinical use. And this is for scanning mice and rats. And the technical co-investigators are myself and George Corner upon this. And what we want to do is that we want to develop an engineering team to run in parallel to the application team to develop some of the technologies that I've talked about and more. I've only got 15 minutes today. And in order to do that, we asked Colin if he would include within that grant application £35,000 for this research package called VADA. And this allows programming of the ultrasound system, so we can program the beamform inside and processing of the received data. So this is incredibly powerful. It will allow us to do things that an average ultrasound machine just cannot do. So there's a fantastic opportunity for Dundee University there. And over the next few years, George and I hope to set up and run that engineering team. So that concludes my talk. I'd like to acknowledge Professor Zhihong Huang for her continuing support. And as Blair said, I also write books.